Hi, welcome to this lecture of CSE351, which is Introduction to Data Science. And in this lecture, we will look at the statistical distributions. So, before that, let's redefine data scientist. So, you'll find a number of interesting definitions for data scientists. This is another interesting definition, which says that a data scientist is someone who knows more statistics than a computer scientist and more computer science than a statistician, which is in a way correct. So that's the responsibility of a data scientist to know uh, computer science as well as statistics. More statistics than a computer scientist and more computer science than a typical statistician. Okay, so now let's look at another very interesting concept of statistics, which is called the central dogma of statistics. So what is it? So usually in statistics, we want to make some statement about a population. So we would like to say something about a population, like what is the mean height of the people in Long Island. That could be an example. Now, the difficulty is that it's not possible to find out uh, the height of everybody in Long Island and then make a statement. And making some statistics on the whole population of Long Island, and then making a statement like, for the men in Long Island, that's the average height, or the height mean of the height, or standard deviation of the height. So these descriptive statistics that we often make is not possible to be done on the whole population. So what is instead done in statistics is that we sample. So when a population is given to you which has a lot of people in there, or a lot of data in there, so what we do, we make use of some sampling technique that will involve application of some probability, and then on that sample we will do some descriptive statistics. So descriptive statistics idea you already have got, so that means you will either compute some centrality measure or spread measure. So the point is, we will be working on a sample because that is feasible. So rather than collecting everybody from Long Island, we will use a better sampling approach, and we'll get a sample of the people, and we'll do our we'll compute our descriptive statistics on that sample. So that's what we do in the central dogma of statistics. Now, using the sample that you have got, now you'll make some inference. Now you'll say something about the population. Alright, so what might happen is that this is a continuous process. So you can see a loop right here. So it may so happen that your population keeps on changing. So you have to go through this cycle. So this is something that should not stop. It has to continue. Alright, so from the population, you will use some probability, get a sample out of it, compute some descriptive statistics using that, make some inference, double check that. Okay, so this goes on. That's called the central dogma of statistics. Okay, now another very interesting thing that we should be knowing, interesting and important, is about the data distribution. So in statistics, and more so in data science, it's very important to have some idea about the data distribution. So you might wonder, like, what is this data distribution? So this relates with the statistics here, and we have already developed some understanding of a random variable. So if you have anything, any event, you're doing an experiment which deals with the probability, then we can come up with some function, if you remember, that can take some values, numerical values, and on the basis of the numerical values that your function can take, you come up with the probability corresponding to that function. So these things we have already looked at. So if you really want to revise that concept, then I'll request you to go back to my previous video lecture where I talk about the random variables. Now, so For a random variable, we will have a corresponding probability distribution associated with that. And the probability distribution will give us an idea like what would be the probability of the random variable when it takes a certain value. Okay, so these things we have done with an example of throwing a couple of dice, and also an example with tossing of a coin. So all that results in experiment, and we can come up with a random variable, and we'll check with the probability, and using probability distribution functions or probability density functions, we will come up with the structure of the probability, like how the probability will vary. Alright, so what we have to do here is to look into some very important and very common distribution functions. So these functions that we will be looking at are binomial distribution functions, the normal distribution, the Poisson distribution, and the power law distribution. So you might wonder, like, why only these four? Do we have more? I'd say yeah, we will have more, but these are the most important, and often a lot of random variables that we come across are easily modeled using one of these distribution functions. Okay, so let's move on and start with the okay, before that, let's see, like, why is there a need for starting these distributions, and what will we gain, right? Why should we study these distributions, and what will we gain out of this once we spend so much of time? So the reason behind that is that, first of all, we already have some classical distributions like the ones that you saw in the previous slide, and most of the random variables that you see around, they fit in one of those. Alright, so the classical probability distributions arise often in practice, so we should look for them, right? So tossing of a coin also belongs to one of those four categories. You will realize that very soon. Okay, so there are already these classical distributions which are given to us, and if we understand those well, then we might be able to map one event that we see around us to one of these distributions. Another interesting thing about these distributions are that we have closed form formulas. So you'll see that for every distribution that I will be telling you about, you'll find a formula for that, which is a mathematical formula which will be based on some variables or some parameters. So we do have closed form formulas and special statistical tests built for those. So a lot of work has been done by statisticians for these distributions, like if your data follows this distribution, so then what statistical test you can perform on your data. So a lot of work has been done for us already by brilliant statisticians. So what we need to do is understand these distributions and try to see if our data fits into one of these distributions. Okay, so now there is a warning which says that, however, your data does not necessarily come from a particular distribution just because, okay, so it's saying that a lot of times we make this mistake. The mistake is because of the excitement. We see that, our when we plot the distribution of the data that we have, it looks like a bell shape, and whenever we see bell shape, we may have this temptation of assuming that this is a bell shape, so it should be a normal distribution. That may not hold. Okay, so that's the warning right here. However, keeping these 2 points in mind, however, your observed data does not necessarily come from a particular distribution just because the shape looks similar. All right. Okay. So now let's start looking at the very first distribution that we have in this discussion, binomial distribution. Alright, so I'll first read this definition, and then I'll give you some example and we'll discuss it further. Binomial distribution corresponds to the situation where you are doing an experiment, and in that experiment you are doing an identical and independent trials, and it has two outcomes. one will happen with the probability of p and the other one will happen with the probability of 1 minus p. And you should understand that p will always be less than or equal to 1. Okay, so one more time let me read it and then I'll come up with an example and we will take it further. An experiment that consists of an identical and independent trials which have two possible outcomes with a probability p and 1 minus p. So example is that of tossing a coin. So let's make it concrete and let's think of a scenario. I'm given a fair coin with head and tail, and the experiment that I am doing is tossing it 100 times. So in that case, n that you have right here will become 100. I'm tossing my coin 100 times. So let's assume that p is the probability of getting ahead. Let me use pen right here. So for my experiment that I have to do, I'm saying that let n be 100. I am doing 100 independent trials and the trial is of tossing a coin, so we are not changing anything, and p corresponds to the event that I get a head. Alright, now what will binomial distribution answer? Now if I'm interested in finding out that if I toss my coin 100 times, then what is the probability that I get? X means number of heads. Here x is number of heads. Now this expression that we have for binomial distribution says that what is the probability that x, which is my random variable, which is number of heads, is equal to 51. So how do you find it out? Alright, so this binomial distribution has this expression or the closed form equations or formula which will help me compute the probability of getting 51 heads when I am tossing the coin 100 times, and these tossing of coin 100 times is my experiment which is identical and independent. If I toss a coin once, it is, and then I toss the coin again second time, then the outcome on the second time is independent of the first time. So on, if I go on doing it, then all these 100 trials that I'm doing, which corresponds to tossing of the coin, these are all independent of each other. Good. So now let's try to understand this formula, which is not difficult, which says that this probability that you have, which is p of x is equal to x, that means small x is 51 here, and the capital X, which is my random variable, let me call that random variable in this situation, taking the value of 51 could be computed as, this is the combinatorial thing which you can write as n choose x, which means n is your what, which should be n is equal to your 100 for this specific example. 100 choose 51. Alright, so this is the combination of coming up with any 51 heads out of the tossing of 100 out of 100 coin tossing. And then since out of these coins I want head to occur 51 times, right? So p is the probability of getting a head. So it should happen 51 times, so you'll have to multiply p with itself 51 times. It can happen in any order. The order is not important, so this is something you need to keep in mind. And when you did this experiment 100 times, 51 times you got a head, and remaining 49 number of times, which is 100 minus 51, you got a tail. Okay, and the probability of getting a tail here is also the same as the probability of getting a head. Okay, so here p would be 1 by 2 and 1 minus p would be again 1 by 2. Alright, so this is very simple to understand and it's a very common process. Like in a lot of places, you'll come across a situation where your random variable would follow the binomial distribution. Okay, and you should understand this condition which says that you have an identical independent trials with two possible outcomes, one with probability p and the other one with probability 1 minus p. Okay, if that is the case, then you can find out the probability of x, which is a random variable, taking any specific value x, finding out like how many times it happened using this expression, like how many times you got ahead. Alright, so now there's another example which follows binomial distribution. Let's have a look at that. Now if you have a player who's a hitter, right, so this player, if he has some probability of hitting the ball as p is equal to 0.3, right, so probability of hitting the ball is 0.3. now 1 minus p you can compute, which is 0.7. and now the scenario is such that when this guy is batting, the person will either hit with the probability p is equal to 0.3 or that guy will miss. So we have two outcomes here, p 0.3, 1 minus p would be 1 minus p. If you compute, that will come out to be 0.7. Alright, so this will also follow the binomial distribution. Okay, and because hitting the second ball is independent of hitting the first ball, right, so all the requirement that we have for binomial distribution would be followed in this case of a batter as well. Okay, so keep an eye on all these kind of scenarios. You should be able to identify whether the situation corresponds to binomial distribution or not. Okay, so let's move on. Now we have this interesting case as I was telling you about, which is the tossing of a coin. So let's pay attention to the curve that you have on the left. So how will this probability distribution function look like? Okay, so in this scenario you have the probability of head turning up as 0.5 and we are doing 200 such experiment, 200 tossing we are doing. So if you look at it, if you do all these experiments and if you plot this this histogram, then you'll come up with this distribution which says that the maximum time you will be getting the number of heads as 100, right, so that will have the highest probability. Whereas if you look at this curve, getting a more number of heads goes down as you move away from this value of 100. Okay, so this is a bell-shaped curve that we have for binomial distribution. You will obtain that once you plot these results. So in case of the tossing of a coin, you have got a bell-shaped curve which is symmetric as well. You can have other situations also which corresponds to binomial distribution, but you may not have such a nice curve like what you see on the left hand side. So as an example, assume that you have light bulbs and you are doing an experiment. So the light bulbs are there and there is a probability associated with the light bulb. The probability is that it may burn out. Alright, so the experiment that you are doing is you have a light bulb, you are switching on and off, right? So you are doing that 1,000 times. Now the point is, we want to find out, like in our 1,000 trials, how many times the bulb burns out. Okay, so the question is this experiment following a binomial distribution or not? So this is something we need to come up with. So when you turn on a bulb, then there are two events that can happen. The bulb may work as usual giving the light, or it may burn out. Now the probability of burning out is pretty low, which is 0.001, but the probability of working normal would be 1 minus p. Okay, so 1 minus p would be 0.999. Alright, so only two events can happen. Either it will burn out, or otherwise it will work as usual. And these events are independent of each other. The trials that you'll be doing, switching on and off, is independent of each other, right? And we have thousands such experiments. So this is in fact a case of binomial distribution. But if you look at the distribution of the probability, like if you are doing that 1,000 times, then the probability that you have one burnout, the probability that you have two burnouts, the probability that you have three burnouts, four or five, in this experiment of doing that 1,000 times is following a different probability distribution. It doesn't look like the tossing of a coin, right? So this is very important for you to understand that, because of the fact that our probability is so low compared to what you see on the left hand side. For tossing of a coin, the probability of the event which is turning a head is pretty high, which is 0.5. And with respect to the probability, the number of trials is decent. Whereas in case of the second case, when you're looking at the light bulbs, probability is pretty low, and as per the low probability, the number of trials that you have is not significant enough, because of which most of the cases, or the probability of not seeing any burnout, is pretty high. Okay, so zero burnout is having very high probability, which is in between 0.35 and 0.40. So if you can somehow increase the probability of burnout, which you may not like to do, or increase the number of trials to millions or billions, then you will have more burnouts, and then this will look more like the symmetric curve that you have on the left hand side. Then you might start with 0, and then you will peak on some burnout frequency, and then it will go down. Alright, so please keep these things in mind. Your distribution might be uh, um, binomial, and it may not look like the bell-shaped curve that you have on the left hand side. Now, interesting thing that you should figure out from the expression right here is that this distribution that you're getting, the probability that you're getting, is a function of n and p. Alright, n and p, because it depends on how many trials you are doing, and it depends on what probability that you have for an event. X is a variable which you will change, and you'll get the corresponding probability. Alright, so this thing is defined, or is a function of n and p. N is the number of trials, and p is the probability of your event, which could be turning of a head or the bulb getting burned out. Okay, so now the next important function, or the distribution, is a normal distribution. And this is a very nice bell shaped distribution, and it's very important because this distribution uh, mm, explains a lot of phenomena that happens in our day-to-day life. It explains a lot of data that we might have around us. Example, if you have the height, right? If you have the data of the height of some community, right? Let's think about the data about the height of some community in Long Island. So if you plot that, then you would find that it will follow the normal distribution. Similarly, the IQ of people also follow normal distribution. So when you're saying height, you might easily guess that even the weight should follow the normal distribution. So there are a lot of scenarios where the data perfectly fits in the normal distribution, and statisticians are often very happy when they figure out that the data follows normal distribution. And I believe a lot of people, not only statistician, even the data scientist, should be happy if she gets to know that the data that she has is normally distributed, because there are a lot of interesting things which we'll look at about normal distribution. Now, the normal distribution also has the closed form formula, just like the way we had for binomial distribution. So, how do we define a normal distribution? So, the normal distribution, which you have here, right? F is defined by these two parameters, which are mean and standard deviation. So the beautiful thing about normal distribution is that you can completely describe a normal distribution with the help of just two parameters, which is mu and standard deviation. Mu is mean and sigma is your standard deviation. So how do you compute, how do you find out this probability? So for that, if you want to find out the probability for x, right, then it is a function of mu and sigma square, which is variance as well. So for that we have a slightly complicated expression, which is 1 divided by square root of 2 pi into sigma e raised to the power minus, there is a minus sign right here, x minus mu square divided by 2 sigma square. So that's the expression that we use for normal distribution. Don't worry about it. Probably you won't have to memorize it, but you should be familiar with it. Like if you see this expression somewhere, you should be able to guess that probably this is the normal distribution. Now there is a warning. Although we know that normal distribution is bell-shaped, we also have seen that the binomial distribution is bell-shaped. Not all bell-shaped distributions are normal. Okay, so please keep that thing in mind. Now, what's the good thing about the normal distribution? Let's look at the properties of normal distribution. One interesting thing is that it is a generalization of binomial distribution. So this is something you may agree, because if you remember the shape of the binomial distribution, that was bell-shaped too. But the value of n, if you looked at, was it depends on how many experiments a user is doing, or a person is doing. So for our case, the two cases that we saw, one was of tossing a coin. We were doing 200 experiments. In the second case, we were doing 1000 experiments. In case of normal distribution, we consider n to be infinite. Okay, that's an interesting thing. And the other thing is that the binomial distribution that we looked at, it had the parameters like n and p. N was number of trials and p was the probability of our event that we were interested in. In case of normal distribution, we have the other two parameters, which are mean, that is mu, and your standard deviation, that is sigma. Now, it's really a bell-shaped, since x here is continuous. So there's another difference that you should keep in mind. The binomial distribution is a discrete distribution. Okay, I'll tell you why discrete. Whereas the x that you have in the normal distribution is continuous, right? So normal is continuous, whereas binomial distribution is discrete. For that thing, let me take you back to the slide here. Look at x, right? What was x here? So when you are tossing the coin 200 times, you want to know what was the probability of getting a 70? What was the probability of getting a 80? What was the probability of getting 90 heads? What was the probability of getting 80 heads? What was the probability of getting 100 heads out of 200? So on and so forth. So if you look at x, then all these are discrete values, right? Discrete values, because it's number of times. The number of times you are getting a head cannot be 25.6 or something like that. It has to be a whole number. Similarly, for the light bulbs also, when you are counting burnouts, then these burnouts would be discrete. they won't be a fractional number. You can't have 2.5 burnouts. Okay, so binomial distribution is a discrete distribution, whereas the normal distribution is a continuous one. Here x is continuous and x goes from infinity in each direction. That means x would be from minus infinity to positive infinity, right? So that's how we will define it. So here the x is from minus infinity to positive infinity. So that's the range for which you will define the whole normal distribution function. Now there's another interesting thing about normal distribution function is that if you have some normal distributed random variables, then their sum would be also a normally distributed variable. Okay, as an example, as we have in the textbook, I believe, if I have the grade of the students in my class and the grade corresponds to different subjects, and if I know that the student has taken 4 subjects in the semester, and the grade of the students are distributed is distributed normally, it follows normal distribution, then when I compute the sum of the grades, or maybe the average of the grades, and then that will turn out to be a normally distributed. That's an interesting thing about the normal distribution. Okay, now this is one of the most important slide in my lecture, I will say, which is the plot of a normal distribution. Look at this beautiful normal distribution. So here it is said that one of the strong points in favor of normal distribution is that it gives the tight bounds on probability. Let's try to understand what is this tight bounds on probability. This is your normal distribution, and in the middle you have the mean, right? The center of your normal distribution is mean, and then you have a standard deviation which is sigma. So now on the x-axis we have points marked as mu, which is the mean, then mu plus delta, that means the region that we have from here to right is 1 sigma on the right hand side of mu, and similarly you have on the left hand side sigma on the left hand side of mu. So this point is mu minus sigma, and here you have mu plus sigma. Let's go further on the right. So you have mu plus 2 sigma and mu plus 3 sigma. Similarly, you can mark these points as mu minus 2 sigma and mu minus 3 sigma. Now, the interesting thing about the normal distribution is that if you have a mean here, then one standard deviation away from the mean, that is this region, which is one standard deviation on the left and one standard deviation on the right, which you have in this pink color, it will have 68.27% of data points. That means the probability of lying somewhere here, which is sigma on the left and sigma on the right of the mean, is 68.27%. So that means there is a high probability of a point being lying somewhere here, sigma on the left and sigma on the right. Okay, so one standard deviation away from the mean has a high probability, which is 68.27. And if you want to move further and want to consider the blue region as well, then it says that the probability of a data being 2 sigma away from the mean is 95.45%. That means the probability of your variable lying in this region is pretty high, which is 95.45%. So this is a tight bound on probability that you have in normal distribution. If you go further down, then in 3 sigma, right? So from mu, if you go to 3 sigma on the left and 3 sigma on the right, that means 3 standard deviation on the left and 3 standard deviation on the right, then this whole region will capture 99.73% of the probability. That means it's highly likely that the data that you have in the normal distribution would lie in this region, which is 3 standard deviation from the mean. So 99.73% of your data that follows the normal distribution would lie in 3 standard deviation from the mean. 3 standard deviation on the left and 3 standard deviation on the right. So which is a very tight bound on the probability by any distribution, and here it's the normal distribution. Okay, so that's what we mean by tight bound on the probability, which is provided by normal distribution. So when we talk of normal distribution, then there is a concept called z-score. So how do we compute z-score? So z-score for any value x can be computed as that x, the value that you have for your random variable, minus the mean that you have, divided by the standard deviation. Okay, so if you have a value of x, then you can find out where exactly that x will lie by computing this thing, which is subtract the mean from x and divide that by standard deviation, which will tell you how far this x is from the mean in terms of standard deviation. Okay, so now let me see what I have in the slide here. Okay, so this is kind of giving you an idea about the distance on x. Mu minus 3 sigma, mu minus 2 sigma, which means 1 standard deviation is the gap. Okay, so the tight bounds on probability follow for z-score from normally distributed random variables. So some example, like IQ is normally distributed. So let's say if somebody is saying that IQ is normally distributed, it could be a question somewhere. So let's try to understand what we can gain from this fact that something is normally distributed. So if I say that IQ is normally distributed and the mean is 100. Alright, so let's put 100 right here, and we are looking at IQ right now. So let's make it more concrete. You're looking at IQ. Okay, so IQ will also follow this normal distribution. Here the mean is 100. Now he's also saying that this mu is 100 and sigma is equal to 15. Alright, and now the point is, let's think about the IQ level of 130. How rare is IQ of 130? That's something we are trying to find out. That the mean is 100, standard deviation is 15. Now what can you say about the IQ level of 130? Is it very rare or is it very common? So to answer that, what we will have to do is, let's map 130 in terms of mu and standard deviation. So 130 is equal to 100 plus 2 times 15. This is mu plus 2 sigma. Alright, which means that you are right here. Okay, so you are right here at this point. You are right here at this point. So what is the probability that you will be here? Okay, you are better than these many people on the left hand side. So your probability should be somewhere on the left hand side. And what is the probability of being in the region outside this, right? So when you are in this region, then that means this region is half of these two, right? So when you are okay, wait a second. So for this case, what we should be doing is, we need to first find out the percentage of people who are below 130 IQ, right? So in this region, if you look at from here to here, these are the people who are less than IQ 130. In fact, this is also the region less than 130 IQ, but the way we'll be computing it, we know about this region only, right? This is something we'll have to figure out later. So this whole region that you have in the middle, it corresponds to 95.45, which I believe we have approximated as 95 in this computation. So let's assume that 95% is this whole region. Okay, 2 sigma is 95. Now whatever is outside this 2 sigma is 5%. Alright, so 5% people, they either have the you know, this 5% corresponds to this region as well as region 2. We are interested in region 2, not region 1. So this region plus this region accounts for 5%, and since we are only interested in the right hand side region, which belongs to the people with higher IQ than 130, it will boil down to 5 by 2, which is 2.5%. Alright, so this information which somebody can give us in the form of the fact that IQ is a normally distributed attribute and its mean is 100, the standard deviation is 15. Now tell us about the IQ 130. What do you think? What is the probability of people having a 2.5 or higher IQ? So this is something we can easily figure out, right? On the basis of this rule, which is also called as 68, 95, 99.7. Why 68? Because in one standard deviation from the mean, you have 68.27% of the data points. That's a probability. It is up to you how you treat it. And why 95? It's 2 standard deviation away from the mean has 95.45 probability. And what's 99.7? That means that the probability of an event happening in this range from mu to 2 standard deviation away from the mean, left and right, is 95.45. And what is 99.73? This is for 3 sigma away from the mean. Okay, so that's a very interesting fact about normal distribution. Okay, so what is not normal? Since there is a tendency that when you see a bell-shaped curve, you might feel that well, great, we got a normal distribution and we know that normal distribution is very nice, let's make use of it. Okay, so not all bell-shaped distributions are normal. Like stock return is something which is not normal. It is in fact a log normal and it has a fat tails. Okay, so the detail of this you will find in the textbook. The stock return means that how much the stock is fluctuating. So if you plot the fluctuation of the stock, it might look like, or it looks like, the bell shaped, but unfortunately it is not normal distribution. Why? Because in the normal distribution, the rare events, they happen very rarely. I mean, the probability of extreme event is very low. Whereas in case of the stock returns, the rare events are still they have still reasonable distribution, which is not captured by normal distribution. So normal distribution is not fit for stock returns. Okay, that is bell shaped, but not like normal distribution. Alright, because extreme events like stock crashing is rare, but it is still common, more common than what a normal distribution will represent, and that in fact is log normal. Okay, so there's another interesting thing which is about the mixture of normal distribution, right? So don't be confused by the fact that I already gave you, which was about the random variables following normal distribution. If you have random variables that follow normal distribution, then adding those random variables will be a normal distribution. But mixture is a different thing. It says that mixture of normal distributions are not normal, right? Like, let's look at this plot that we have right here, which should explain. You have the normal distribution about the height of women. Similarly, you have a normal distribution which is explaining the height of men. Now, if you have the mixture of these two population, women and men, and you're thinking that if you have the height of these two population together, then that will also follow the normal distribution. This is wrong. Okay, so you can very much see from this plot itself, which explains it. This is a normal, the other one is a normal, but this doesn't look like a normal, right? You have a bump kind of a thing right here. This is peak, but this is a bump kind of thing. So the mixture of normal distribution are not normal. Okay, so don't get too much into the details, but keep this thing in mind that mixture of normal distributions are not normal, whereas if you have the random variables which are normal, then their addition will result in a normal distribution. Now there are a few facts, like there are statistical tests which exist, which will help us in identifying whether the data that you have is really drawn from a normal distribution or not, right? So if you are worried about it, like, it looks like bell shaped, I thought it should be a normal, how do I check whether the data that I have which looks like a normal distributed is normal or not? Then to answer that question, we have a solution. There are statistical tests which we can use to find out whether the data that we have is normal or not. Okay, now to another interesting distribution which will be used to find out the distribution of lifespan. So there are a lot of cases where you might be interested in finding out the probability of the lifespan of something, right? So let's think about the lifespan of an organism, or maybe of a human being. Okay, so how can we model that? So we are looking at a distribution which can model the probability of something surviving for some specific days. So how do we model that? For that we have this notion of probability p, that's one parameter, like the way we had it in binomial distribution. Now we are interested in finding out n, like what is the probability that this guy survives for n days, till n days, right? So it's again very simple. If you know a little bit of probability and if you try to reason, then this is straightforward. Now for a lifespan of n days, that means if the person has to live for n days, and let's make that concrete, right? Let's not say a person, let's think of an insect that has a very short lifetime, maybe some 10 days, so 15 days. And if we have 15, we want to find out that there is a butterfly. I'm not sure about the lifespan of a butterfly, but let me assume that it is not much. And I want to know what is the probability that this butterfly will survive for 15 days. So a simple probability will say that if this butterfly has to survive for 15 days, and if we know that p is the survival probability, p is the probability that this butterfly will survive on a single day, probability of surviving single day, right? So when you're saying 15 days, then that means you need to survive the first day, second day, till 14 days, right? This is 14th day. So this in total you need to survive for 14 days, and then let's say, okay, the butterfly may die on the 16th day. So when the butterfly is dying, it should be 1 minus p. Probability of surviving is p, then the probability of dying should be 1 minus p. Alright, straightforward. So this is very simple. Ideally you should remember these things, but even if you don't remember, I think you can reason it yourself. Okay, so that's the distribution for the lifespan, right? Can we use it in other case also? Yes, you can use it for the example of the bulb as well. If you know the probability of the bulb being dying, the probability of survival we knew, which was no, we didn't know the probability of survival. We knew the probability of the burnout of a bulb. So 1 minus probability of burnout would be the probability of survival of the bulb, and you can apply that on this expression to find out the probability that for how many hours this bulb will survive. Okay, so this is an interesting distribution which can be applied in a number of cases where you are interested in finding out the probability of a lifespan. Okay, let's move on. Now we have another interesting distribution which is called Poisson distribution, and this distribution is also given to find out the frequency of the interval between some rare events. Okay, so this is where you might need some attention. Others were comparatively intuitive, but this distribution needs some attention. Poisson distribution measures the frequency of intervals between rare events. So let me try to explain this from the example of the bulb. So we have bulb, we are using it, and then there is an event where the bulb may burn out. Alright, so the bulb burning out is a rare event. So what we are doing, we have bulbs, we are using the bulb and monitoring like when exactly is the bulb burning out, and we'll note down the time when the bulb burns out, and then we'll replace that with a new one. So the rare event right here is the event of bulb burning out, and the interval that we are monitoring, which we are kind of interested in analyzing for the distribution, is the time between the two burnouts. Alright, so the interval here would be the time difference between the two burnouts, right? So how do we compute that? How do we represent that in Poisson distribution? For that we have another closed formula that goes like the probability of x is the lifespan. So what is the probability that my bulb would survive for 200,000 hours, right? So the x right here would be the number of hours, the probability of this interval that you want, which is 200,000, is a function of mu. What is mu? Okay, so mu is your mean lifespan. Okay, so in order to answer this question, which is the probability that my bulb that I just bought would be there for 200,000, I can answer that only when you provide me this information that what is the mean life of the bulb that I got. Okay, so if you say that the mean life of the bulb is 250,000 hours, then I'll plug that in and I can compute that. Okay, so that's the important parameter that we have. E raised to the power minus mu raised to the power x divided by x factorial. So for this I believe it is difficult to reason how did we arrive at this expression, but just keep that in mind. Okay, so instead of probability P, the distribution is parameterized by mu. Okay, and mu you can compute mu by this expression. So I should make a note right here that you should not be scared by these expressions, and probably you should not try to memorize but should try to reason. Okay, good. So let's move on. I hope that these things are making sense, although these are a little mathematical. Now you should wonder, like, find the previous case that you explained to me makes sense, but now the example that I am about to give you is a case which is a little difficult to understand, but this Poisson distribution explains this phenomena pretty well. So if somebody wants to find out the distribution or the probability of kids in a family, right? So the distribution of kids per family also follows Poisson distribution. That's an interesting thing which might need some reasoning, right? So The way it has been explained in the textbook is interesting, and I kind of follow. So the way we can interpret the kids in the family is something like, an interval between two rare events, right? So the rare event could be the first rare event when the first kid was born, and then the last rare event would be when mm, the last kid was born, right? So this interval here in the case of the kids in the per family corresponds to the number of kids that people have in the family. Okay, so somehow you need to reason it, somehow you need to fix it in your mind that here the number of kids in a family corresponds to the interval between two rare events, right? And when you want to find out the frequency or the distribution of the interval between two rare events, then you use Poisson distribution. Okay, so this distribution fits perfectly fine, for the number of kids in a family. Okay, so this is something you can see right here. All right, so the interesting fact is that the average US family has 2.2 kids, so which is something you can see right here also. The highest probability that you see here corresponds to 2.2 kids. Okay, now another interesting distribution, which I believe you might find in a lot of real life data sets that you may work in data science domain, is called power law distribution. Okay, so how is the power law distribution expressed? It has a form like this. It has the form that the probability of x is equal to c times x raised to the power minus a, where a is some exponent, right? So now if you want to understand this thing, then you'll find out that the probability when the x is really low is pretty high, and as x increases the probability goes down because x has an exponent which is minus. All right, so x goes down as to the power of a. Okay, so this will go down exponentially. That's how the power law distribution is defined, and a lot of situations you'll encounter where your data would in fact follow the power law distribution. Okay, so now there's some interesting thing about power law distribution. Here the data in the power law distribution does not cluster around the mean. Now if I ask you like what are the distributions where the data cluster around mean, you should say normal distribution. We have just seen that. All right, so in case of power law distribution we don't have that scenario. You'll see that it's a very strange kind of a distribution where we don't have the situation like normal distribution where a lot of data is clustered around the mean. And here it will have in the normal distribution, you will find that you'll have very large values as well. In case of normal distribution, we did not find very large values. The values that you have are mostly confined in 3 sigma. Uh, you know, is confined 3 sigma away from the mean each direction, which was 99.7% if I correctly remember. Okay, so now you should be wondering like fine, you said that the power law distributions are common, but what would be the use, like in which scenarios can we apply? So some scenarios which are very common and that these scenarios reflect a lot of situations is 80-20 rule. So let's try to understand what is 80-20 rule. Right, so 80-20 rule could be defined something like that, that 20% of x gets 80% of y, right? So this is a very general statement. Let me make it concrete. So 80-20 rule could be something like that. If I say that 20% of people or 20% of population is controlling 80% of the wealth in this state or in this country, so that is an example of 80-20. 20% people who are rich are having 80% of the wealth in New York City or maybe New York State. That kind of a statement. So if you have any statement like this which describes the data, then that data follows a power law distribution. Okay, so let's look at some interesting data sets to understand this power law distribution. So if we look at the population of the cities that we have in USA, so the average, let's look at it from a standard distribution, probability distribution function. So the US city has the average population size is 165,719. Now the interesting thing about the city population, if you look at, if you're given the data about the population of the cities in USA, then the interesting thing is that the standard deviation that we have is based on some data set, which I'm not sure is recent, but anyway, the same should be true with the recent data as well. Now the average is 165,719. But the standard deviation is 410,730. Look at the value, standard deviation is more than the double of the mean, or at least double of the mean, more than double, I'll say. Okay, so this is a strange scenario, right? Cannot be explained by normal distribution. Your mean is less than standard deviation. Standard deviation is huge, right? So with this scenario where your mean is less than the standard deviation, what will you say about the cities with really high population size, right? So if you're thinking of representing this data with the normal distribution, it's not going to work out. All right, so that's the message, and it has to be explained by a different distribution like power law distribution. All right, so interestingly, if you look at New York City, then the New York City has the population like 8 million, right, which is much more than the mean. Okay, and you can find out, right, if you are really thinking about somehow forcing it into normal distribution, you can divide this city of you should first subtract the mean from and this population, and then you should divide by 410. You'll find out how many standard deviation away the population of New York City is from the mean. All right, so yeah, it's a point like why is this a really bad idea to think of representing the city population using the normal distribution. And one more fact about the scenarios where power law distributions work is something like where the rich gets richer. All right, so very interestingly discussed in our textbook is the fact that why the cities have so much of a population. Why is the population in New York City so much? Why are people still coming to the New York City when we don't have much space and all? So the phenomena is such that more people attracts more people. Okay, a lot of population attracts more people there, and there are a lot of reasons behind the attraction. More people means more avenues, means more job, more opportunities, and that's kind of phenomena which is pulling people in, and that's resulting in the power law distribution. So same kind of scenario applies to similar domain, right? Okay, good. So I have some examples. I'll go over those examples and I'll explain to you what I mean. So when you plot the population, right, so here if you look at the left plot, we have the population of the cities, and then on the x-axis you have the rank. So 50th most populous city you have right here, and it has a population like this. And then the first city I think we don't have, because it's not possible to get the whole data if you keep the city with the highest population. So this is the power law distribution. Okay. So now one interesting thing about power law distribution is that when you plot it on log scale, that means log of x and log of y, then it tends to give you a straight line, which is a characteristic of a power law distribution. When you transform the original plot in log, that means log of y and log versus log of x, you tend to get a straight line. Alright, so right here on the right hand side we have the log plot for the city population data. Okay, so this one, right, the biggest city values are out of scale, so for that reason you don't see the bigger cities, you see the data for 1 2 3 4 5. So maybe the 10th, after the 10th city you have 20th city or something like that. Okay, so this is an interesting thing actually, for which I did this. I have these mathematical calculations which highlights a very interesting fact. So please have some patience and follow along. So what do I have here? This px is equal to cx raised to the power minus 1 is the power law distribution. Let me confirm. Yes, cx to the power minus a. That's the case. Now what will happen if we increase the value of x? Okay, so this whole exercise is to understand the power law distribution from the wealth point of view. You have the data about the people and their wealth, and we want to understand that the distribution from the power law. Okay, so it's an interesting exercise. So the if you have x as the wealth of a person, then how is that being represented? The probability of a person with the wealth x is equal to c into x to the power minus a. Now let's double x. So if I have the wealth as x, I want to know that what is the probability of finding a person with the wealth twice the person and the wealth, right? So initially you have x, I will double that to 2x. So now I should be doing probability of 2x is equal to c, and in place of x I have 2x now, 2x raised to the power minus a. Let's simplify that. You'll have c and 2 to the power minus a and x to the power minus a. Let's further simplify it. So it will boil down to 1 divided by 2 times a, c x to the power minus a. Okay, so what is happening here, the probability that you had, right, was c x to the power minus a right here. Okay, so that was px. So if I want, I can put a px here, right? So when you double the wealth, what you did, you doubled the wealth. The probability of finding a person with twice the wealth has gone down by a factor of 2 to the power a, right? So you're multiplying that probability px by 1 divided by 2 to the power a. Okay, so it has gone down by a factor of 2 to the power minus a. Alright, that's the same thing. So that's the power law. If you double the wealth, then the probability of finding a person with double the wealth goes drastically down. That's the power law distribution. Okay, in terms of the wealth. So we are discussing it in terms of the wealth. So these things I've got from the textbook, and I found that interesting, so I'm discussing that. So if you want, you can write this factor that you have 1 by 2a as an f. F is equal to 1 by 2 to the power a. And for wealth, f is found out to be 1 by 5, sorry. Alright, so when you double the wealth, then the probability of finding a person with double the wealth goes down by 5, by a factor of 1 by 5, right? Okay, so if you followed this thing, if you followed the fact that if you attempt to double the wealth of a person, then its probability is going to be reduced by a factor of 5, then let's try to understand the discussion here. And I will start from bottom up. right? Let's look at this one. If you know that, right, if you know that 625 billionaires have 5 billion each, right? So there are 625 people with the worth 5 billion. And now if you want to find out how many people I'll find with double the worth, which is 10 billion, then this thing will go down by, will be divided by 5, right? You know this factor 1 by 5, right? We figured out, we know about the F as 1 by 5 for wealth. So if you know that 625 billionaires have 5 billion each, and you want to find out how many billionaires have 20 billion each, then that number will go down by 5, right? So you have 125. If you say that I know 125 multi-billionaires have 10 billions, I want to find out how many super billionaires have 20 billion. So this thing is to be divided by 5 again, because that 1 by 5 is the constant factor. Alright, so you get 25. Now you say that 20 billion means super billionaire. Let me define hyper billionaires with 40 billions each, right? So again, this has to be divided by 5. You end up with 5 hyper billionaires. If you say, okay, fine, let's go to the extreme. Now I want a person with 80 billion. Okay, so 1 by 5, that means there's only one person that has 80 billion worth, right? So this is an interesting thing that I found, and I believe that if you do this exercise, you will understand what this power law distribution is in terms of the wealth of the people. Now, same thing is being explained here in a general term, which says that what is the power law? As you multiply the value by x, what we are doing, x is our wealth, right? We are multiplying that by 2 every time we are doubling it. You divide the value of people by y. People means 625 and y is 5. X is 2 in our case, right? It should make sense now. Alright, so definition of power law, we have this thing again, kind of explaining the same thing that I'm trying to communicate to you with the help of some examples. Now for a power law distribution, distributed variable x, the probability that x takes an x value is equal to c into x raised to power minus a. The constant c is unimportant for a given a. This constant c ensures that the probability sums to 1. So as you saw in the work that I did, I kind of ignored c. We were paying attention to a. So the reason why we have c right here is that we know that when you sum the probability and then over the values of x, then it should result in 1. So just to make sure that when you integrate this probability over the values of x, it should result in 1. For that reason we have this constant. Alright, yeah, so c is unimportant for that reason. We have c here just to ensure that the probability sums to 1. Now this is something I already worked on. When you double x to 2x, you reduce the probability by a factor of 2a. We worked that, right? So larger values keep getting rare at steady, non-decreasing rate. Alright, that's the same thing. Now there are a lot of scenarios where you will find the power law distribution. Let's look at some. So okay, I'll follow these ones. Internet sites with X links, they also follow power law distribution. What does it mean? Well, that means like how popular are the internet sites. So if somebody gives you the sites and maybe the number of users who are visiting the site, and if you plot that, then you will find that this plot will follow the power law distribution. Now you need to wonder, like, why exactly do we have this distribution for internet sites? Well, the reason being that the sites are popular. Like, as an example, Facebook, right? Why is Facebook popular? Probably there are a lot of friends of ours who are using Facebook, right? There is a lot of activity there. So it somehow started. It started someday when the first time Facebook came into existence, and then people started joining in. Then more people started joining in. So this was a kind of social network phenomena where um, say 100 people joined initially, then um, more friends of these 100 people joined in, friends of friends joined in. So it's a kind of exponential kind of a growth, which kind of explains that why these internet sites with the number of inlinks, means number of people visiting, number of people logging in, is showing the uh, power law distribution. Okay, so similarly, I'm not very sure about earthquake, so I'll skip that. Word use in the words usage also follows a power law distribution. Okay, so there's another thing actually which we I think already looked at. Power law shows a straight line on the log value, log frequency of loss, right? So when you do log, then log distribution, then you should find a straight line. Something I showed you when we were doing the population plot, the city population distribution. There's another interesting principle which is about the word frequencies, and it's by Zipf's. So Zipf came up with a very interesting law that says about the relative frequency of the popular words. So the law states that the kth most frequent word is used 1/kth as often as the most popular word. So this is also a kind of power law distribution, which says that if you rank the words, so here we have 100 most frequent words in Wikipedia, then here D is the most frequent, and then you have of and all that. So it seems to me by this law that the second most frequent word, which is of, which is sorry about that, it is an of. Now the second most frequent word, which is of, will happen 1/2 the number of times the most popular word, which is the, has happened. Alright, so Zipf's law is also an instance of power law distribution. Here we have A is equal to 1. So a word rank 2/2 will have the frequency. I think there's some problem with this slide. Wait a second. Let's say keep, and this needs to be pushed a little bit. Okay. Alright, so Zipf's law is a power law for A is equal to 1. So word of rank 2x have half the frequency of rank x, right? So this is what the, sorry about that, this is what this Zipf's law is all about. Alright, so that's what it says, that the kth most popular word or most frequent word is used 1/kth as often as the most popular word. And what you have right here is also the same thing, which says that it's a power law for A is equal to 1. So a word of rank 2x have half the frequency as the word of rank x. Alright, so there are some interesting things about the power law. Here the mean makes no sense, right? So for power law distribution, you should see that we are not using mean in any way to define the power law, right? In that expression that you have, which is c x to the power minus a, you don't have mean anyway. Mean is making no sense here, unlike the normal distribution where mean was very important. Why so? If you look at the wealth data itself, and if you find out the mean, then the wealth of Bill Gates itself will add $125 to the US mean wealth, right? So that means here for power law distribution, um, the wealth of the richest person will change the wealth of everybody by, all the individual in US by $250, which doesn't make much sense. Standard deviation also does not make sense, right? Which we already have seen in that example of the city population. Median is better, but I won't consider the as important as the other factors. Now, the last point is that this distribution is scale invariant, which means that if instead of considering all the, let's discuss that from the city population point of view. So when we were looking at the city population, I told you that we don't have the data for the top uh, few cities, because if you have those top few cities, you may not be able to get the complete data, or the data that we have. So even then, if you confine yourself to just one portion of this city data, say you're interested in only looking at the top 300 to top 600 cities, the range of 300 to 600 cities, and you want to explore what is the distribution, you will still find the same distribution. The original distribution and this truncated distribution that you are kind of zooming in, they will all look the same, right? So that's the point about the fact that the power law distribution is scale invariant, meaning that zoom in region will also look like the whole plot. Alright, so that's it. I will stop right here, and I'll see you in the next video lecture. Bye bye. Take care.